I love geology for two main reasons. You can tell amazing stories about our geologic past, stuff that happened long ago, and if you have the right field evidence, you can tell a pretty good story. But the story has to fit the field evidence that's been collected. The second thing I love are unsolved mysteries. And there are plenty of unsolved mysteries in geology in all branches of the sciences. And tonight's topic, great earthquakes of the Pacific Northwest, have both of these things. Stories from the past and unsolved mysteries. There's a chance that down the road, people are going to look back on us here in 2016 and kind of shake their head. Kind of go, those poor people. They knew a great earthquake was coming, but they couldn't predict when. In other words, I think there's a chance we might eventually crack the code on how this works and be able to predict when the next great earthquake will happen. But maybe you're really super skeptical of this great earthquake thing altogether. And what the hell is a great earthquake anyway? I thought we just dealt with earthquakes in Seattle and San Francisco. Great earthquake, is that anything different? And then it gets kind of distorted. We start talking about, have you heard a great earthquake is going to make a giant tsunami and it's going to crash onto the shores of Washington and it's going to get as far inland as Seattle and it's going to wipe out Seattle and Portland. How much of that is true? Is any of that true? Everything west of I-5 will be toast. So some of you know what I'm talking about. There was an article last summer written in the New Yorker magazine, a large platform, reached a lot of Americans. The article was beautifully written by Catherine Schultz from New York City, and she was writing about the Pacific Northwest. And I was astounded, I think I'm still astounded, at the reaction of Americans to that piece. And you may remember some of that. There were weeks and weeks and weeks of people just freaking out. Like, my God, Seattle and Portland are going to be wiped off the map? There's confusion. There's like, huh? So what I want to do tonight on the chalkboard and then with our visuals is to try to separate the fact from fiction. To try to go to the field evidence, because this is important. If you're a good science person, you're true to the field evidence. Your interpretations are based on the field evidence, and as new evidence comes in, you change your interpretation to fit the evidence. It doesn't work the other way around. You can't tell a story and then cherry pick the evidence you want to fit your story. We've got to be true to the evidence. We've got to be true to the evidence. So that's what we're doing tonight. And I will try to help you at least see where the evidence is for all of this discussion. Hysteria is too strong, but discussion. And we can decide together, or maybe I'll let you decide, what the evidence is saying to you. So, I've drawn this beautifully crafted map of the lower 48 states about an hour ago on the chalkboard. Do you recognize it? This is not Alaska, this is the lower 48. And what I've written here in the back, you can't see these numbers, but these are the years that we've had magnitude 6.5 or greater earthquakes on the San Andreas Fault in California. So, first of all, I'm just trying to picture the general American and what their general perception of earthquakes is in the lower 48. And I think immediately they go to California. And these are all dates that are real. These are all earthquakes on the San Andreas Fault in California that have happened, greater than 6.5 magnitude, in the last 200 years. So this is clearly an earthquake issue. And California is known as an earthquake state. And it happens that there's millions and millions of people living right on this fault. It's the San Andreas Fault. It's a plate boundary. The North American plate is moving west. The Pacific plate is moving northwest. Those plates are trying to grind past each other. And when there is an earthquake on the San Andreas Fault, there is a segment of the fault that releases energy. There's no physical evidence to suggest that the entire length of the San Andreas Fault goes at once. There's no evidence for that. But individual segments have ruptured in the last 200 years. And some of those segments have gone more than once in the last 200 years. Now, if you go further east, and again, I'm just trying to get a sense of why there was such surprise and reaction to Catherine's piece. Some, especially further east, know about the Missouri earthquakes. In 1811 and 1812, there were 3 large earthquakes that killed some people. Still kind of unclear what happened there, so we're not going to try to address that. That's still a bit of a question mark. And there was one big earthquake in Charleston, South Carolina in 1886, also a question mark. Here's my first point of tonight. I think Kathryn Schulz's piece in the New Yorker caught people by surprise because they didn't realize, first of all, that earthquakes were even an issue up here in the Pacific Northwest. And maybe their thinking was, does the San Andreas Fault go up to the northwest then, if we're talking about earthquakes? And why is Kathryn in this article talking about tsunami? Nobody's talking about tsunami with the San Andreas Fault. And yet we're not only talking about a megaquake, but a killer tsunami as well. This is confusing. So, does the San Andreas Fault come up to us? It does not. But we do have a plate boundary that looks like this. So that's the San Andreas Fault, a plate boundary. This is the Cascadia subduction zone. It's a boundary between the Juan de Fuca plate, an oceanic plate heading towards us, and North America again is going to the west. This is a 700-mile long crack. Couple of important differences, though, between this crack and this crack. The San Andreas Fault is vertical. It goes 60 miles down. It's a true plate boundary. This is a plate boundary as well, but it's not vertical. It slants into the ground to a particular direction. Guess what direction? This crack, which looks like it's offshore, and it is, angles down into the earth beneath western Washington, western Oregon, and northern California. The fault is beneath Seattle. It's beneath Portland, 20 to 30 miles down. Another important distinction before we start talking specifics. I already mentioned that there's no physical evidence that the entire length of the San Andreas Fault has ruptured. But there is overwhelming evidence we're going to look at tonight that our entire 700-mile fault has ruptured in complete length. Let me say that again. We're talking, you got to wait. When? So I'm whetting appetites, I guess that's a good thing. I'm trying to hook you. This is different. We've got an entire full rip. In fact, there's a beautiful book written by Sandy Doughton from the Seattle Times called Full Rip 9.0, which has a lot of detail that I won't talk about tonight, but she did a beautiful job. This is a book written by Brian Atwater, a guy we're going to feature as well. This is a free book called The Orphan Tsunami of 1700. It's available online to download for free. So some of the data I'm sharing with you tonight are from those two books, but there's other things as well. Who am I, by the way? I'm a teacher. I teach at the college in town. I don't do any of this research, so why the hell am I even up here? I have practice teaching science to a general audience, and I'm surrounded by people in our department who are very bright people, many of whom are directly related to this story, this research group. So they're keeping me honest, they're helping me with this data, and we can make this work. Okay, let's get into it. If you've been to these other lectures down here, you have heard earthquake talks before. And so we've got to make sure we separate out the great earthquakes from the others. By the way, here's another way to make sure we know about a great earthquake compared to a regular-sized earthquake. That San Andreas Fault I just erased, generally the quakes on the San Andreas are magnitude 7.0. Give or take a few points in the scale, but roughly, let's just for simplicity's sake, 7.0. We're talking about 9.0 earthquakes up here, possibly even higher than 9.0 on that fault that I just erased off the coast of the Northwest. So 7, 9. Those numbers are pretty similar for most of us, but let's think carefully about this scale. The rule is if you jump one whole number on the Richter scale or the moment magnitude scale, jump one whole number from 7.0 to 8.0, we increase the energy released by a factor of 30. 30 times the energy is released with a magnitude 8.0 than a magnitude 7.0. What we're talking about tonight, great earthquakes, 30 times 30, 900 times the energy released with a magnitude 9.0 compared to a magnitude 7. Okay? Great earthquakes means great. Audience participation, I like it. Okay, so I promised evidence, right? We haven't done much evidence yet. Let's get there. The field evidence is what we want. So some of you are familiar with a diagram that looks like this. This is a cross-section of the state of Washington and offshore. This could be Oregon or Northern California as well. Here is the Juan de Fuca plate. It is subducting. It's ocean crust. This is the sea. This is the ocean. Here's ocean shores. Okay? Here is the Hal Holmes Center in Ellensburg, Washington. That's where we are. Let's put Seattle in here as well. So we need the Cascade Mountains between, that's confusing. We need the Cascade Mountains between Ellensburg and Seattle, and we need a mountain range, don't we, between Seattle and ocean shores. The Olympic Peninsula and the Coast Range. I think many Americans assume that Seattle is at the coast. But there's a whole mountain range, as we all know, between ocean shores and Seattle. Okay, so what are the earthquakes we're not talking about tonight? Well, old-timers in the room remember Seattle 1949, Seattle 1965, Seattle 2001, roughly magnitude 7.0. This is the Nisqually earthquake that happened more than a decade ago. These are all earthquakes that are happening regularly within the subducting Juan de Fuca plate at deep levels. We're not talking about those tonight. We don't understand them anyway. What else are we not talking about here? There's a whole cluster of shallow crustal earthquakes that routinely happen in shallow levels within the state of Washington. The most famous in geology circles is the 1872 earthquake that happened north of Wenatchee, Washington, along the Columbia River, south of Chelan, north of Wenatchee. We just found the fault scarp a couple years ago. We, meaning the researchers now, you understand that. It's the royal we. The Seattle Fault has been found shallow levels beneath the city of Seattle. That last produced an earthquake, roughly magnitude 7.0, 900 AD, the year 900 AD. So we're not talking about these guys either. We're just talking about the great earthquakes, the one that have 900 times the energy released that these guys do. So where are we making those great earthquakes? The answer is out here underwater. That's why we're talking about tsunami. And this boundary here, this boundary between the Juan de Fuca plate and this is the North American plate, of course, that's moving this way. So we have a convergent plate boundary, two plates that are hitting head on. We're getting these great earthquakes because this boundary is locked. This boundary is stuck. Let's put the word locked. This is our model to fit the field evidence, which I haven't shared with you yet. I'm doing it backwards. I'm giving you the story and then I'm giving you the evidence. But I'm promising you the evidence is coming. Our model is, since I have this sketch up here for us, that every 500 years, that's the first big number for us tonight, every 500 years in Washington, we have a great earthquake somehow related to this locked zone. By the way, this business about have you heard, what did he say? It's like a game of telephone, right? You hear something and then you repeat it and it's slightly different than what you heard. By the time it comes back around to you, it's different. This business of us being overdue for the next great earthquake keeps coming up. Are we really overdue? Well, you just heard the number I gave you, which is the most conventional number used at our latitude off the coast of Washington. Every 500 years. Does anybody know the last time one of these great earthquakes happened? Not 500 years ago. The answer is 316 years ago. On the night of January 26th, the the year 1700, at 9 o'clock local time, this locked zone became unlocked. And this entire boundary failed and released 900 times the energy of a magnitude 7.0. Now, how in the world do we know that? That's a whole nother lecture. But once we get to the visuals, you'll see in Brian Atwater's work with these sand sheets at the coast, and he did some detective work to figure out the day and time. Let me repeat it. The last time a great earthquake happened in the Pacific Northwest here, January 26th, the year 1700. That's 100 years before Lewis and Clark. We don't have any written records of that thing. We've got Native Americans who have oral traditions of that terrible night, and a tsunami for sure arrived. So if you're an old-timer in the room and you say, this is all baloney and I don't remember a big earthquake, you're right. You don't remember the big earthquake. You weren't around. Nobody was around to write this down. But the evidence coming will show you that. So, one final point before we move on with this sketch. When we unlock this boundary, what are we locking and what are we unlocking? The idea is that if we lock this boundary and we subduct the Juan de Fuca plate, the leading edge of the North American plate is going to be dragged down gradually with the subducting plate. So think 500 years of gradually pulling the leading edge of the North American plate down, like loading the end of a high dive at a swimming pool. And we finally have so much energy stored in that coiled spring that we release the energy probably in about a 4 to 5 minute span. We release the energy in a 4 to 5 minute span. That's the earthquake. And we restore the leading edge of the North American plate back to its original position. We displace a bunch of ocean water, and that's why a tsunami is part of this story. Now, I promise data. Here you go. The last time this kind of earthquake happened in the world was when? In Japan. The year was 2011, March of 2011. You remember Fukushima, you remember the nuclear power plant, you remember the tsunami, maybe more than you remember the earthquake itself. That's because the engineering of the buildings in Japan is superior to most places in the world, and they did not have colossal failure of their buildings from a magnitude 9 earthquake. But of course we remember the tsunami waves that crashed into the coastlines of Japan. Here's the exciting part scientifically, even though we're talking about a tragic afternoon in Japan. There were GPS receivers in Japan, instruments anchored into the bedrock. For the first time, we had a way to measure how much the crust moved during a great earthquake. And a colleague of mine, Walter Zaliga, as an academic exercise, let me repeat, as an academic exercise, this is not a prediction, as an academic exercise, took all that GPS data from over here in Japan, how much the ground moved. He mentally brought it over the ocean to Cascadia, our subduction zone. He flipped it around because our subducting plate is oriented the opposite way. And he took those numbers from Japan and plotted them on this diagram. I want to do that for you right now. You got what we're doing? We're taking the Japan measurements of crustal movement and plotting them here to give us at least an idea of what is possible if we have a similar magnitude 9.0 release. Ready? The instruments that were underwater in Japan, right down here by the trench, moved 150 feet. The crust underwater, when we release the leading edge of the overriding plate, moved 150 feet. Last time I checked, that's half a football field. That's 50 yards, moving in 5 minutes. That's why we're generating a tsunami, by the way. These are real numbers coming from real instruments in Japan. Let's continue. Walter took a town in Japan, X number of miles inland from this oceanic trench in Japan, and then found one that is analogous to our ocean shores. So in other words, the GPS station in ocean shores, you know what we're doing, right? The number 50 feet. Ocean shores, the town moves 50 feet in 5 minutes westward and simultaneously moves 30 feet down. There is audience participation reaction right now. A Japanese town far enough inland to be our Seattle. You still know what I'm doing, right? Don't be confused now. 6 feet of moving trenchward towards the trench. And even Ellensburg. In other words, a Japanese town 250 miles inland from the trench. That's our distance. We're 250 miles from this oceanic plate boundary. Even Ellensburg moves 10 inches. Hal Holmes moving 10 inches to the west. Fred Meyer, D&M Coffee, Central, everybody, the whole valley moving 10 inches to the west. So this is, in a 5-minute span during a magnitude 9 earthquake, opening Washington up like an accordion. And the closer you are to the handle of an accordion, the more you're moving. The keyboard is, you don't play accordion, how would you know? What a dumb idea. You can picture what I'm trying to say, right? These are real numbers, and they are cause for pause, if nothing else. Let's keep moving. Let's do a map now of the Pacific Northwest. And now what we're interested in looking at is what? How do we know we're overdue? Are we overdue? Where is that evidence coming from? How do we know these great earthquakes have happened? That was Japan we were looking at. How about here? This is Washington, this is Oregon, this is California. Here is our trench, our plate boundary, our fault with a 700-mile length going from off the coast of Vancouver Island down to Northern California. It's not an accident that the Cascade Range, which have active volcanoes, the length of the Cascades perfectly match the length of the trench. It's a 1-to-1 correlation between subduction of the Juan de Fuca plate, JDF, and the North American plate, which at our latitude is moving kind of to the southwest. So we have a northeast-southwest collision. Cascades. Let's throw in our secondary mountain range. Again, maybe news to many Americans. Seattle is not at the coast. We have the Olympic Peninsula. We have the Coast Range of Oregon and Northern California. Okay, good. So let's put in Seattle. Let's put Seattle up here. Ellensburg. Let's put ocean shores. And Interstate 5 runs right through here. Interstate 5. What's the phrase? Everything west of Interstate 5 will be toast. That was a direct quote from Catherine Schultz's article, a quote from an emergency official, a FEMA person. Now, what does that mean? What does toast mean? Who's doing the toasting? I'm not joking in this case. Is it the tsunami? Is that the toast? Is that the distress? Is there a tsunami getting as far inland as I-5? No. I'll show you the evidence in a second. For sure, no. Is the ground shaking vigorously enough with our 5 minutes of that kind of crustal movement we were just talking about? I could buy some of that, I suppose. And that's really not what I'm trying to do tonight. But tsunami getting that far inland, no. How do we know? If I do this, and I just do a little squiggle, that's about the width of the tsunami hazard zone in the Pacific Northwest. I could maybe do a little squiggle coming in the Strait of Juan de Fuca as well. Now, how can I be confident of that? There are deposits. There are tsunami deposits, sand layers that tell us for sure that a tsunami got that far inland. And those sand sheets, those sand deposits, are only found the width of that squiggly line. So let's get away from a tsunami coming into Seattle and wiping it out. Let's get rid of that right away. Is it possible that a tsunami reaches Seattle? Yes, but only after a magnitude 9 releases the earthquake, releases the energy, generates the giant tsunami. We'll talk about how giant is in just a second. Coming through the Strait of Juan de Fuca, and by the time it works its way into the Puget Sound and gets as far south as Seattle, it's been modeled that most of the energy of that tsunami is dissipated. It's gone. And so to put two and two together. Tsunami, destruction in Seattle. Back away from that, please. Let me summarize the data, though, that this has happened multiple times in the past. What's this? The great earthquakes magnitude 9. Brian Atwater was the pioneer with this 30 years ago. He dug into estuary muds, and he found mud. 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 5,000 years worth of mud, either by being exposed during low tide, think Willapa Bay or the Neowayakam River or the Copalis River, take your pick if you know that country out there. You're digging for clams, it's muddy, right? You step in, you got your hip waders on, you sink in way more than you want to. You need help to get out. It's mud. But in that mud, Atwater was able to find distinct layers of sand. And sand should not be in that muddy estuary. Something energetic brought the sand in. And sometimes it's not a sand layer, but it's a sudden change in the details of the sediment being deposited. In other words, Atwater found good evidence for sudden land level changes, buried soils, and occasionally a sand sheet. He has 9 of them, 9 sand layers stacked one on top of another in the last 5,000 years worth of mud. That's evidence because at many places along this coastline he kept finding those sand layers, the same sand layers, old friends. And so this is a regional story. There's actual sand being deposited by a tsunami, so it's not a figment of our imagination. Major tsunamis are part of our history, but again, not big enough, not nearly big enough to cross into the Puget Sound or the Willamette Valley. We can go back 10,000 years in time if we leave the shore and go offshore, under the water of the Pacific Ocean. What are these? I'm not much of an artist. You got to guess what these might be? They're not currents. They are canyons, underwater canyons. They're impressive. I'll show you a couple of maps. We have bathymetric mapping of these enormous canyons, think the Grand Canyon, underwater, offshore the Pacific Northwest, okay? Canyons. Research ships, mostly operated by a guy named Chris Goldfinger, now there's a name, Chris Goldfinger from Oregon State University, has spent the last 20 years or so going out by boat, sending a piston core down into the floor here, and drilling, coring into the sediment that's at the foot of each one of these submarine canyons. There's a big pile of sediment underwater at the foot of each of these canyons. And the sediment, it looks like, has traveled down the submarine canyon. So think an underwater landslide. We all know what a landslide is. Think of it happening under the ocean. And having that landslide with all these different sediment sizes hurtling down this submarine canyon. It's hugging the bottom of the water, and density is pulling it down the slope. Goldfinger, I'll try to make this quick. This could be a whole lecture. Goldfinger has found exactly 19... I got to tell you what a turbidite is. Hang on. I jumped the gun there. Turbidite. So I can do the same kind of sketch for what Goldfinger is finding at each one of these spots. You know what we're doing now, right? We're coring the bottom of the ocean. Not the bottom, but on the slope of North America. Similar to Atwater, he's finding mud, 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 and the mud came down the canyon, came hurtling down the canyon, or came down in a pelagic form. But Goldfinger started running into this same idea, that we have these distinct layers of sandy material punctuated by centuries of mud. It looks different though than here because this is an underwater landslide. So if we enlarge this, there's coarse sand at the bottom of one of these layers, coarse olive green sand, gray mud on both sides. And the sand is getting finer and finer and finer. I'll show you some photos in a second. So this is a graded bed. This is coarse sand grading up to fine sand in one of these layers. This is a turbidite. So to review, in case I'm losing some of you, if you have an underwater landslide down a submarine canyon, when that underwater landslide comes to rest, a graded bed called a turbidite is the result. Okay, how in the world does this have anything to do with our great earthquakes? Here's how. 10,000 years worth of mud, the same 19 turbidites have been found at every one of these sites. That's big. Let me repeat that. In every one of these major canyons, at the floor of every one of these canyons, there is sediment that came down. And in that 10,000 years of mud, there are exactly the same 19 turbidites in every one of these locations. So what caused an underwater landslide to come down every one of these canyons at the same time, simultaneously? Because the dating has come in, and they're not only the same 19, but they're the same age. They match ages as you go from canyon to canyon. This is a regional story. This is the best evidence we have that these are full rips on occasion, that we're having seismic shaking along the entire 700-mile length of this boundary. Still with me? So, that's where this number of, well, let's talk about that number. So if you take let's do it this way. How much mud? 10,000 years. How many turbidites? Anybody with it? Good. Woo! Wow. 10,000 years of mud, 19 major turbidites. If every major turbidite is a great earthquake, then we have roughly 500 years, a little bit more, but roughly 500 years. That's where that number is coming from. An average of 500 years between great earthquakes coming from this. But the plot thickens. And now we get to the mystery part before I'm almost done with the chalkboard. Mystery number one. Goldfinger has found an additional 22 turbidites in this 10,000 years of mud just off the coast of southern Oregon and northern California. Let me repeat that. We got 19, the same 19 all the way from Vancouver, BC down to northern California, but there's an additional 22 turbidites just off the coast of southern Oregon and northern California. So that equals, help me out, 22 plus 19? 41. If we do 10,000 divided by 41, we now have a recurrence interval of 243 years between earthquakes. Are you catching what I'm saying? If that's accurate, and we have an average of 243 years between great earthquakes instead of 500 years between great earthquakes, who's overdue? It's been 316 years, right? The overdue statement is maybe more applicable to the residents of southern Oregon coast and northern California coast, and 500 is maybe more applicable to us here. This is vigorously debated currently, the meaning of Goldfinger's turbidites, to the point of, are there really additional 22? Do we really need an earthquake with each of those extra 22? And there's a few who are very skeptical and even are not so sure that we've got 19 and we need a great earthquake for each of the 19. So this is one of those areas that I love, unsolved mysteries. And I think that in the next 2 decades, we will have much more data from the submarine sediment, perhaps from different research groups. And if they're all pointing to the same conclusion, they're all finding 40, whatever it was, then we can be sure we've got a 243 recurrence interval. That's a major mystery. I got one more mystery for you, and then we go to the visuals. Thank you for your energy. This is great. You want a mystery? I got another one for you. That was kind of a wimpy mystery. I got a good one for you. Some of you have heard this before, but you maybe haven't heard this twist before. So here's Washington, Oregon, Northern California, which is suddenly fatter than it should be, California. There's our boundary once again. What's happening? The Juan de Fuca plate is subducting beneath. Let me give you a little cutaway as well. So this is a cross-section of the same thing. Got it? Map, cross-section. Okay? There are 500 GPS stations that are currently working in the Pacific Northwest. Global Positioning System. Some of you have heard of these. There's dots all across. I'll show you maps. Dots all across the Pacific Northwest. That's one of the claims to fame of the geology department here in town at Central. They process the data coming in from each one of these stations. Every half a second, there's data coming into these stations. Where's the data coming from? Satellites, 3 satellites, are measuring their distance from satellite to one station in Wenatchee, Washington. And if Wenatchee crust moves slightly, just a fraction of an inch, we can show that. We can measure that movement. So we can measure tiny movements in the Earth's crust by monitoring the data coming in from these receivers, these GPS instruments. Good? One of the big surprises is that after 20 years of data coming in from these receivers, there is a beautiful, graceful, clockwise rotation of the Pacific Northwest crust. This is data coming in from all of those receivers. The longer the arrow means the faster the rate of motion. Let me give you an example. Ocean Shores, remember our friend? There's a GPS station right south of downtown, booming Ocean Shores. It's moving 3/4 of an inch every year to the northeast. And you might be going, well, wait a minute. I thought you said the North American plate was going southwest, and it is. This is a moving tectonic plate, but within that raft, we have this intracrustal deformation. We've got crustal warping within this moving raft. 3/4 of an inch to the northeast in Ocean Shores. Portland, GPS receivers, 1/4 of an inch to the northeast. Here's the mystery. This clockwise rotation is ongoing. Every year, 3/4 of an inch. Every year, 1/4 of an inch. Ongoing. That's not the mystery. Every 14 months, a handful of stations stop. And they even go back a fraction of an inch for 2 weeks. And then they start going again. And another cluster of a dozen GPS receivers stop and back up. In other words, they go southwest for just a bit. And then they continue on. What is going on? That's data that we're still trying to interpret. Here's our model. It may have something to do with predicting the next great earthquake. It might. This is another active discussion. Depends on who you talk to if this is promising or not. So you remember our locked zone? And down dip, so here's the hard part. Let me make a better sketch for you. We're almost done with the chalkboard if you're getting bored. LOCK. So on the top of the subducting Juan de Fuca plate, it's locked for a certain length on the top of that boundary. But if we go down dip, if we keep going down on the surface of the subducting plate, the next section of the top of the Juan de Fuca plate is a transition zone. And the GPS stations that are doing this weird stopping and going back for 2 weeks, and then 14 months of going ahead, and then 2 weeks back, da, 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 da. I stole that from Bob Butler in Portland. It looks, or idea is, that there is energy being released, that we're actually slipping the boundary. I thought it was locked. It's locked up here. But perhaps this regular 14-month event, called an episodic tremor and slip event, an ETS event, perhaps that is happening by releasing energy and slipping the surface of just a patch of this subducting plate. So in case anybody's still with me, if we can imagine looking down through the North American plate, can you just use your X-ray vision now? We're looking down. So the Juan de Fuca plate is diving beneath, right? And 20 miles down is the surface of the Juan de Fuca plate. Beneath extreme western Washington and Oregon, we're on top of the locked zone. But if we're further east and we're looking down through the 20 miles worth of North American crust, we're getting to this belt where we get this crazy, repetitive story. Here's the payoff for including this in the lecture. Is it possible that one of these events where we're having some slow slip, is it possible that is a trigger for the whole lock zone to unlock? Is it possible that this slow release of energy somehow ratchets things up in the lock zone? Another musical analogy. Let's forget accordion now. Let's go something else. You play guitar, you're tuning your guitar, and you are tuning your string. And each ETS event, we're tightening our string just a little bit more. Oh, I got to get that string up a little higher. I'm not quite to the pitch. Is it going to snap on me? That's the question. That's the analogy. Is each ETS event tightening the string just a little bit more? Is it loading the locked zone a little bit more? So during that 2-week window, there is the energy equivalent to a magnitude 7.0 that is released gradually over a 2-week window. And nobody pays attention. Nobody knows except the GPS receivers. They can pick it up. So that is a potential point of discussion as well. So here's a current map from the USGS warning about earthquake risk, and the red areas are at higher risk than other areas. So here's that South Carolina and Missouri, and of course our friend the San Andreas Fault. And notice that our red zone, our high danger zone, if you want to think of it simply, does not go all the way up to us. So this is factoring in Goldfinger's additional 22 turbidites. And so this map may change as we continue to go. So this is the article, again, beautifully written by Catherine Schultz, but it's the reaction that is striking to me. This is in California. This is the fault, a vertical plate boundary. The North American plate's on your right, the Pacific plate's on your left. Look at how clean that is. These two plates are shifting laterally. And remember, it's a segment at a time that releases energy and makes earthquakes in Southern California and Northern California. Gorgeous image from the San Andreas Fault by Scott Kronk. Thank you, buddy. Do we believe these headlines? Is somebody trying to sell me something, you're asking? Should I really be all freaked out? Should I not? Should I ignore all of this? This is my favorite subheading. Worried Pacific Northwesterners seek reassurance from geologists who are the worst people to ask for reassurance. Let's go to the evidence. Juan de Fuca plate, that's what it looks like. Here's our fault that we now know is angling beneath us. And when you plot the earthquakes in recent memory in the last 200 or 150 years, this is comforting. We don't have any earthquakes out here, so I guess it's good news. But we're just not going back far enough in time. This is Seattle, 1949, downtown, and if you're remembering these kinds of earthquakes, and I don't want to minimize this, there were a few fatalities and structural damage, etc. But if you're remembering this and thinking, well, you know, we handled the great earthquakes before, we did fine. This was a magnitude 7.0, roughly, not 9.0, and we now know the difference if you didn't know the difference before. These are the current numbers based on the field evidence. So in the next 50 years, this is peer-reviewed journals now among geologists, a 14% chance in the next 50 years of a full rip of the plate boundary. A partial rip, again, Southern Oregon, Northern California, the odds are higher. These shallow faults we haven't talked about tonight. The deep faults like the Nisqually quake we haven't talked about either. There's that book I mentioned. I strongly recommend purchasing it. It's a wonderful book. One of the diagrams that I am particularly fond of is one of the simplest. We're not only showing the Juan de Fuca plate from Sandy Doughton's book, we're showing the surface of the subducting Juan de Fuca plate, and that's the surface area that is rupturing for a great earthquake. Brian Atwater, the guy that got this started 30 years ago, he was out at these yellow circles here along the coastline finding what? Finding sand in places that sand should not be located. This is the sand that came in 316 years ago. And you can follow that sand layer all along the Pacific Northwest coastline. It's real. It's not an idea. There's field evidence for that. And again, we are out here. You may have heard of the ghost forest. Groves of trees that are dead. They've been dead. They were killed by the great earthquake. They were killed because the land at the coast suddenly dropped. And that happy tree became a sad tree, became a dead tree in the centuries that followed. Also at every one of these yellow circles is the sand. And notice that the sand is deposited irregularly over this very rich organic topsoil. That's the idea. We're dropping the land suddenly. Why? We're locking for 500 years, we're unlocking, and the coast is suddenly dropping because of the rigidity of the leading edge of the North American plate. Look at the level of preservation. This is Brian's slide. This gray stuff is the tsunami sand that came in. There's individual surges of tsunami waves. This is like a delicate fossil in the mud. This is a clump of marsh grass that is overridden by that water coming in on that terrible January night, 1700 AD, 100 years before Lewis and Clark. Fantastic field evidence. You can't tell anybody that there hasn't been a great earthquake in Washington. But you can go deeper. This is a place you would go, explore, canoeing, hiking, clamming, whatever. This is what a guy like Brian can see and what he can find. 5 sand sheets, dates for each great earthquake. There's some plus or minus error bars here, but these are real dates from dating methods and other things. So let's look at these. Here's 1,000 years between great. I thought it was an average of 500. Yeah, it's an average of 500. We have less than 500 between some of these others. So we can't be too comfortable with our 500 number, as evidenced by these 5 most recent great earthquake land level changes. How'd you do with your visualization of the locked and unlocked? Does it match this? We pull the rigid North American plate down with the subducting oceanic plate. We're locking the boundary, and as we pull this down, we're going to gradually raise the coastline. After 500 years on average, we release the energy and we have a sudden land level drop at the coast. Tsunami generated by that sudden motion. Remember our 150 feet of movement? That was right out here, right at the trench when we restore that motion. 150 feet of motion in 5 minutes in the Tohoku, Japan earthquake. So this book, what I mentioned before, free, available online, written by Brian and some Japanese colleagues, tells the story of how they came up with this precise timing, which is a beautiful piece of detective work in geology. Now, in the last 60 years, we've had 4 of these great earthquakes worldwide: Chile, Alaska, Sumatra, and Japan. And each of those had a tremendous tsunami that crossed the Pacific Ocean or the Indian Ocean. Look, in the case of the Chile earthquake, it takes almost a full day. It takes 23 hours for that tsunami to cross the Pacific Ocean. And in 1960, from the Chile great earthquake, people were killed in Japan almost a day later. And people have telephones and televisions in 1960. I used to show this in my class before Sumatra, and my students would gasp at this because they had never heard really of a tsunami. And does this really happen? Does this really cross the Pacific Ocean? And in the last 15 years, we've had 2 of these, and now we have video of this. So it's less of a mystery than it used to be. Yes, these happen regularly and presumably have been happening throughout the history of our planet. Some of you know that when there's a great earthquake and you're walking along the beach, the first thing to happen is the water pulls away. And of course, humans want to go down and explore all these flopping fish. But that's a bad move because you've got about 20 minutes on average, 20 minutes from the ground shaking to when the tsunami water comes in. And of course, it's not just kissing the former shore, it's coming much further inland. And look what it's leaving. Sand. There's our sand sheet deposited by a tsunami. So this is 2004, the day after Christmas, a great earthquake, a locked zone that became unlocked. 230,000 people killed. I'm sure these folks did not make it. I don't know the story of retrieving this camera, but this is the initial tsunami waves coming in Thailand. And so what we're talking about off the coast of Washington is a perfect example of what happened here. A full rip of a segment of this subduction zone, and this is the Indian Ocean now. So people are getting killed on other shores of the Indian Ocean hours after. And this is 2004 now. There was no tsunami warning system installed at that time. And then, of course, we go to Japan. GPS receivers. As we mentioned, the first time we were able to measure the amount that the ground moved during the earthquake itself. And here's a GPS receiver in Japan that is showing the movement. As we have our locked zone, we're now subducting beneath Japan, and our receiver gradually is getting pushed inland and up. And that's what we're experiencing during the 500 years of locking in North America. I'm not sure of the average number over there. When we finally unlock the boundary, remember ocean shores? 50 feet trenchward, 30 feet down. That's the documentation in Japan. So, the GPS receivers in Japan before the earthquake and after the earthquake. And you want to know how much motion that is? I gave you those numbers. Those were the numbers that Walter helped us with and brought them over to Washington. So we have a GPS network as well. We've got red dots. We've got these instruments that are recording that. And Walter, the guy that did the work, took all those vectors you just saw in Japan and flipped them around and plotted them in western Washington and western Oregon. Notice that the length of the rupture in Japan was a shorter distance than our 700 miles. So it wasn't a comparable full rip for our neighborhood. But you can see our 10 inches of movement in Ellensburg and up to 150 feet of movement underwater. This is what a GPS receiver looks like. And now we want to talk briefly about the tsunami and the size of the tsunami. So the trench is out here. Here are the canyons, by the way. See Washington, La Push, Neah Bay, Moclips, Ocean City. You've got your bearings. We can't have a tsunami cross this mountain range and get into Seattle. But we can have one of those tsunami come in through the Strait of Juan de Fuca. These are tsunami hazard maps that have been created by geologists. So if you can't see this well, this is Willapa Bay, so North Cove and Grayland and South Bend. And these areas in kind of light orange are likely to be overrun with tsunami from a magnitude 9.0 earthquake. Long Beach, most of the Long Beach Peninsula, completely overrun. Ocean Shores, Westport, do you know these countries well? Hoquiam, Aberdeen, all within the tsunami hazard zone. And I've got two more YouTube clips for you, very briefly, to show you some of the modeling. It's beautifully done, and these are brand new. I just found them last night. Let's watch this one. A hypothetical. There's lots going on here. I'll shut up and let you just absorb it once. We'll try it again with some narration. Grays Harbor, Long Beach, Westport, Ocean Shores. Look at all the complexities with these tsunami waves. It's not just one wave, it's a multiple set of waves. Let me try to show this to you again. The red and the purple are the highest waves. The purple, they are modeling up to 36-foot waves, the purple. And the yellows are down to about 15-foot waves. And so, obviously, if you're right down there at the coast, it is not a good situation. Let's try one more. This one looking more carefully at the potential of sending a tsunami into the Strait of Juan de Fuca and how close we're going to get to Seattle. So here's the Strait of Juan de Fuca, the boundary between Washington and British Columbia. Seattle's down here. And we've got waves again. I can't read that quickly enough. But these are the highest waves coming in. Whidbey Island, there are tsunami sands from the ocean at Whidbey Island, and a few other places along both sides of the strait. But by the time we get to Seattle, we've dissipated much of that energy. And again, these models are based on the tsunami sand deposits that have been found by Atwater and friends. The submarine canyons, that needs a little bit. I got about 5 minutes left. Hang in there. Washington, Oregon, Northern California, here are those canyons crossing down. And this canyon goes out hundreds of miles, by the way. But if we really look carefully, every one of these dots is where Goldfinger or Griggs or Adams have drilled into the sediment associated with these submarine canyons. And remember, the same 19 are found. The same 19 turbidites are found in every one of these cores. And that's what gets us to our average of 500 years between events, at least at our latitude. Is this what you had in mind? Underwater, submarine canyon, landslide down through the submarine canyon, and the deposit that rests after the event, after the landslide is done, is this graded bedded sequence. This is one turbidite. And if we can get dates on the turbidites, we can get dates on the earthquakes, potentially. Core to core to core, from Vancouver Island down to Northern California, you can follow those turbidites like old friends. There's Mazama ash from Crater Lake in each of those cores. The date for the Mazama ash is roughly 7,700 years ago. So that was a time horizon that was used to keep track of where we were in the mud. There are 13 turbidites on top of the Mazama. 19 total if we go back 10,000 years. Oh, sorry, I got one more. This is a good one. This is Goldfinger taking all of his work thus far and plotting it in a little movie with dates. So this is from all of the turbidites that have been found and dated. This is 7,630 years ago. 7,180 years ago. And do you see what he's doing? He's giving us a date and giving us whether it was a full rip or a partial rip. And he's doing that by finding these additional turbidites down here off the coast, where this is Northern California and Southern Oregon. Here we are up here in Ellensburg and Seattle, and Ocean Shores would be here. So you can find this on YouTube, Chris Goldfinger, Cascadia Rupture Series, I think it's called, and follow this along. I did get an email from him this morning. I found this last night and sent him a quick email hoping he would reply. He did. I noticed that one of his turbidites is the same age as the Mazama eruption. And this is a question that comes up, at least for me, regularly from folks I talk to. Isn't it possible that one of these great earthquakes could trigger a volcanic eruption? And my answer has always been, can't rule it out. No physical evidence thus far to prove that there's a connection. If Atwater's turbidite is a perfect match with Mazama, and it's proven that the Mazama ash came in during the turbidite, then there could be a connection. He claims he has one more possibility, a Mount Adams eruption and a younger turbidite layer. That's very sketchy. Way more work needs to be done. I thought I'd mention it very briefly. Okay, to wrap up, we got to go to the ETS story very quickly because it's one of my favorites, and then we'll call it a night. So here's that clockwise rotation that we've been talking about, documented by the GPS movement. Every red dot in the northwest is giving us this information. Here's a GPS receiver we have anchored at the top of Mount Olympus into the sedimentary rock up there. Mount Olympus is not a volcano. Here's a GPS receiver just above Wenatchee. Every one of those stations is reporting movement, and here's this clockwise rotation. Everybody's rotating around Pendleton, Oregon for some reason. Even in Northern California, rotation to the northwest, rotation north, rotation northeast as we get up to Washington. Here's an animation from Bob Butler's group down in Portland. Pendleton, we're going to rotate around Pendleton. A block in the Sierras, a block in Oregon, a block in western Washington, being driven by the oceanic plates, the clockwise rotation within the Pacific Northwest. Who cares? Why are we talking about it tonight? Because of that weird thing, right? Every 14 months, if you are above the transition zone. So give yourself a try here. Can you do this one last time? Juan de Fuca plate is at the surface. Juan de Fuca plate begins diving at the trench. Juan de Fuca plate in the green zone is locked. X-ray eyes, get rid of the North American plate. We're looking right at the surface of the Juan de Fuca plate. It's locked here. It's locked here. It's locked here. But the red zone is the transition zone, the top of the Juan de Fuca plate that has this weird, slow, silent release of energy. And it's the GPS stations just above the red that are doing this. So locked, green, follow the surface of the Juan de Fuca plate further down dip, and we're emitting these tremors and getting this funky behavior with the GPS stations. This particular station is the most famous. It was the first station where we detected this. A Canadian geologist noticed that the ALBH station on Vancouver, right by Victoria, stopped moving every 14 months, and he figured something must be wrong with his instrument. And he tried everything to figure it out, and then finally realized that all these guys were exhibiting this strange 14-month periodicity. So this is the last animation I have for you. The locked zone, the transition zone, and a slip zone down here. A GPS receiver above the locked, above the transition, and above the pure slip zone. And we're going to plot what these stations are doing, and I'll try my best to help you make sense of this. We'll put it into motion. So the station out here above the lock zone is going to be moved inland and up. We've already talked about that, right? We're crunching the leading edge. So that's inland and up. But above the transition zone, every 14 months, stop and go back a fraction of an inch. Stop and go back a fraction of an inch. And this is what we visualize happening at the transition boundary. Movement and then a little bit of release. Movement and then a little bit of release. Back here above total slip, there's no signature whatsoever. So there are mysteries that remain. Are these ETS events a potential trigger? We'll find out as the research continues in the decades to come. Potentially, this is a key part of looking to the future and anticipating when the next great earthquake will be happening. Your awareness was brought and elevated by Catherine Schultz's article last summer, July of 2015. And we'll continue with the data, we'll continue with the research, and I'll bet you we'll get closer and closer to the truth. Thanks very much for coming tonight. Really do appreciate it.